Okay, so as I mentioned before, efficiency is measuring how much energy is actually useful compared to how much energy is supplied to the device. So meaning, when the load takes energy in, what percentage is actually being converted into useful energy. So anytime you have a conversion of energy where you're going from one form to a different form, so let's say electrical energy to light energy, you actually always will have some amount that is useless or unusable. So for example, if we think back, I always use light bulbs here, but if we think back to a light bulb, the light is what we actually want, right? It's the type of energy that we are trying to get out of a light bulb, right? That's its purpose. However, if you've ever touched a light bulb, please do not touch a light bulb, but if you have in the past, you'll also know that a light bulb gets warm, right? It lets out heat energy. So heat, we don't light a light bulb for the purpose of getting heat out of it, right? We would use a heater or use a furnace, right? So that's not its goal. The goal is to produce light. So the heat that comes off of a light bulb is what we call useless, or we call it unusable energy or unuseful. So, pardon me. So what happens here is the percentage of light that's actually produced is what we call its efficiency. So let's say we have a light bulb that has 10% efficiency. What that would mean is 10% of the energy that is transformed is light energy, and the other 90% is wasted energy in the form of heat. So the higher the percentage for efficiency, the better that device is at using it for useful or its purpose energy. Okay, so for example, we have an old clothes dryer that uses 800 kilowatts per hour, and a new, more efficient clothes dryer will only use 300 kilowatts per hour. So it's using less energy to do the same amount of work, meaning the efficiency is much higher in the newer dryer because there's less wasted energy. So obviously with technology, usually the newer devices are more efficient than older ones. So let's say you have an older laptop and maybe a sibling or somebody else in your family has purchased a newer laptop. What you'll find is the battery that's in the light bulb the battery that's within the laptops are actually becoming more and more efficient and better at being recharged. So when you have older devices, typically in the long run, they may actually be cheaper to purchase, but you end up costing more in the long run because it's using more energy as wasted energy. So having a newer device is typically more efficient and uses up less energy in the long run, right? So it'll take less energy to recharge your laptop, and then you can use your laptop usually for longer periods of time without the battery dying, right? It's just, they keep getting better and better. The technology continues to progress, so we end up having more efficient devices. And that goes for everything: stoves, fridges, televisions, hair dryer, like I mentioned, light bulbs, right? So every type of load that we use energy for are becoming more and more efficient as time goes on. Now, how will you know if you have an efficient device? Okay, so when you start to purchase your own appliances, so in the future, when you go to the store and you're like, I need a new microwave, and you're making a decision on what type of microwave to buy, you might not remember what Miss Henson said about electrical efficiency from grade 9. But what they have is, especially in Canada, right, we have these things called EnerGuides. Okay, and it's actually part of the federal government mandates that all Canadian appliances, or sold in Canada, I should say, have one of these at the store that you can look at to make your decision. So essentially what it will do is it will tell you how much energy it is using per hour, so kilowatt hours. And actually there's this, I'm not sure if you can see it. Let me get rid of this for a second. There's this like gray scale. See how it goes from light to dark? This also will give you a range in terms of showing the efficiency. So the closer to the left side of this bar an appliance is, the more efficient it is. Now, when you go to make a purchase, there's a lot of things to decide, of course, but usually the more efficient appliances are more expensive on first glance, like I mentioned before. But in the long run, you got to think, well, how long am I going to have this microwave? Am I going to have it for, 5, 6, maybe 10 years? How much energy is it going to save you in the long run compared to other types of microwaves? So there's a lot of kind of factors that have to go into this, and maybe, the look of it and all the other kind of superficial things. But in terms of cost and efficiency, those should be coming up when you are making decisions in the future. All right, so here we go. I mentioned you needed your calculator. So here's our first formula for this lesson. There will be another one coming up. So when you're calculating the efficiency of a device, it's based on percent efficiency, as I mentioned. And really, it's just a ratio. It's a ratio from the electrical energy to the transformed energy. So the value that goes in the numerator, or on the top part of this fraction, is the energy output. So this is the useful energy that we want our load to produce. So let's say we're talking about a light bulb. The number that would go on top would be the light energy, because that's the whole point of having a light bulb. The denominator, or the number that goes on the bottom here, is the energy that is used in terms of electrical energy. So this is the energy that it takes in, and this is the energy that it puts out. So this is the energy in terms of electrical energy. The number on top is always the amount of converted energy. Now, another thing that will maybe help you while you're doing this is the number that is on top should always be the smaller quantity, right? You cannot have more than 100%. So the smaller number will go on top and the larger number on the bottom, which will help us here. And then, of course, this is a percent value. So after you do this division, so you divide these numbers, you multiply by 100 to get percentage. Okay, so we'll do some examples. So again, we're going to use grasp here. A light bulb uses 100 joules of electrical energy and produces 35 joules of light energy. Calculates the percent efficiency. Okay, so we are given electrical energy. So that is the energy input. So I'm going to use a capital letter E, and I'll put the little in to signify that it's input, and then the other one will put a little out for output. So 100 joules of energy is going into the light bulb. The energy we're getting out of it is 35 joules of light energy. And we are looking for percent efficiency. I'm just going to use a short form for efficiency here. Okay, so the formula we are using, percent efficiency, is equal to energy out over energy in times 100, which is what we had on the previous slide. So in this case, let's solve. So we have 35 joules over 100 joules times 100. So we get here, if you calculate this out, 35% efficiency. Okay, 35 divided by 100 times 100, you should get 35. And then we have a little therefore statement. The bulb is 35% efficient. Just something short and sweet. Okay? So if you want to pause the video and give this one a try on your own, I think that's the last one before cost, yes. So pause the video, give this a try, and then come on back and then we'll see how you did. Okay, so let's see what we have. So it says a toaster oven produces 850 joules of thermal energy, right? So heat. So keep in mind, that's what the toaster oven is meant to do. So that's our energy output. 850 joules. And it says that the toaster oven has 26% efficiency. So they're giving us the percent efficiency. Calculate the energy that the toaster uses to operate. So what they're asking us for here is the electrical energy or the energy input. So remember the formula is percent efficiency is equal to energy out over energy in times 100. So we're going to have to kind of work backwards here. So let's plug in our information. So energy out is 850 joules over energy in times 100. So you have to basically do some algebraic rearranging here. So first, let's get rid of this times 100. So you always do the opposite function. So if this is multiplied by 100, we're going to divide by 100 on both sides, right? Whatever you do to one side, you do to the other side. So we end up with 0.26 is equal to 850 joules over energy in. So now at this point, we have a couple of options on how to do this, but essentially we can do cross multiplication. So what that means is we can do 0.26, so the numerator on one side times the denominator on the other side. And then the opposite, the numerator on the other side multiplied by the denominator times 1. So in this case, right, we have 0.26 times energy in is equal to 850 joules times 1. Now we want to isolate for energy in. So remember, you do the opposite function. So right now it's being multiplied by 0.26. So we're going to divide by 0.26, and whatever you do to one side, you do to the other. So our final answer here to solve for this is going to be 850 joules divided by 0.26. So let's calculate that. So 850 divided by 0.26. So we get a value of 3,269.2 joules as our final answer. So when you're working through this, the best thing to keep in mind is when you're isolating for a variable is to always do the opposite function of what it is with. If you have something that is being multiplied, you divide. If you have something being divided, you multiply, right? So you do the opposite. Okay, so now we're looking at the cost of electricity. So we'll do this in our last part for this lesson here.